So hello everyone. Thanks for joining. So yeah, thanks also for the introduction and also for the possibility that I can speak here today and give this talk. It is a pleasure. Today's talk will be about progressive JPEGs in the wild and its implications for information hiding and forensics. As Jana said, this paper was presented at the Information Hiding and Multimedia Forensics Information Hiding and Multimedia Security Workshop in Chicago this summer. The research is joint work together with Rainer Böhme. Let's get into it. Let's get started. So the JPEG standard has different modes of operation. There is its baseline, the sequential mode that you can see on the left of the slide, which stores the data in an image in a way so that it is displayed from the top to bottom along the scan line. On the other hand, in the progressive mode, which you can see on the right side of the slide, the image data is stored in a way that allows a decoder to display a blurry version of an image first and then progressively increase the image quality as more data is received. This is useful whenever images are sent over slow communication links, for example, when we're using our mobile devices and have bad reception. Now, let me briefly recall the JPEG compression pipeline so that we can understand it better. So the first thing that we do is we have an input sample and we do color space transformation. So we convert the color, so we convert our sample from the RGB to the YCBCR color space that allows us to separate the color information from the luminance information, so the light and the dark information in an image, because we can then subsample the color information because our eyes are just not as sensitive to changes in this color in the color channels. In the next step, we divide our images into pixel blocks of size 8 × 8, and then we apply a discrete cosine transformation to it. And the result of this are called DCT coefficients, and these DCT coefficients are then quantized, so we reduce the precision, so they are divided by a given quantization factor and then rounded to the nearest integer. Then we arrange our quantized DCT coefficients in zigzag order, and we do run length and Huffman encoding. The decompression reverses those steps to the extent possible. Right, now to better understand it, we can use this cube as a visualization of our JPEG image. On the vertical axis, we have our quantized DCT coefficients in the zigzag order, and on the horizontal axis, we have the precision of these coefficients from the most to the least significant bit. And towards the back, we have all the blocks that are contained in this image. Now, the progressive mode partitions the image data into so-called scans, and how exactly is defined in a scan script. We can see here an example scan script on the right of the slide, right side of the slide, of six scans. Let's see how that works. So the first scan, the initial first scan, transmits all our DC coefficients, so all our DC information, except for the least significant bit. Now, if we would decode this scan alone, it will result in an image showing the average color per block. Now, the scan 2 contains all the first two low-frequency AC coefficients, except for the 3 least significant bits. Now, scan 3 contains all the remaining AC coefficients, again, without the 3 least significant bits. And so on. You can probably get the idea already. After all scans are received, the image does not differ from an image that was sent sequentially. Now, right now, as I told you, the progressive mode has been part of the standard since the beginning. So we wanted to know if it is actually used or not. And to find that out, we did an ad hoc crawl and we collected roughly 200,000 images sampled from historical JPEGs on the 5,000 most visited websites between 2005 and today. And we can see that nowadays, approximately every third image on the web is a progressive one. Now, we also Googled and we found developer blogs from blog entries from Yelp, from Instagram, from Twitter, and also from Facebook, stating why they are adopting the progressive mode for their applications. Now, if we look back at the plot again, we can see an increased share of progressive JPEGs after the year around 2014. And this is also the year when MOS-JPEG was introduced. So MOS-JPEG is an open source JPEG compression library, which is designed for web publishers. It tries to increase the user experience by decreasing web page loading times. Now, I told you that it has been in the standard from the beginning, but yet the multimedia security research community has not really looked into it. And the reason is that I told you that after all scans are received, the image does not differ from a sequential one. But is this actually true? Let's have a look. So what we have here is the libjpeg library. It is the de facto state-of-the-art compression library, and it also supports the progressive mode. Now, if we instruct it to compress an image progressively, we can see that we can save some file size. Now, if we use MOS-JPEG, which outputs the progressive mode per default, we can decrease the file size even further. Now, how is this done? Well, it outputs the progressive mode per default, so it does some scan script optimization. We'll talk about that later. But also, it introduces a novel rate distortion optimization. And what you can see here in red are the pixel blocks that differ in at least one DCT coefficient between the MOS-JPEG and the libjpeg image. So to answer the question that we have in the title here, do progressive images differ? Well, yes, potentially, they can differ. And this brings me to our contributions. So first, we identified the root causes for the artifacts that are introduced by the MOS-JPEG library. And then we discussed the implications these have for the fields of steganography, steganalysis, and for digital image forensics. And we start with MOS-JPEG. So what you can see here is the JPEG compression library. As I explained it before, we have an input image, we do some pre-processing, we apply DCT, then we quantize, and then we arrange the quantized DCT coefficients in zigzag order, and we encode it using Huffman and run length encoding, and then we save the file, the image data to a file. Now, MOS-JPEG, of course, modifies this. So here in orange, we can see that MOS-JPEG implements what I talked about, the rate distortion optimization that is based on trellis quantization, and it uses a perceptual model for this. And also, as it uses progressive mode per default, it implements a scan script optimization, but we will talk about that later. And we will start with the trellis quantization or optimization. So assume this size distortion space. Trellis tries to move each block in the image towards the left on the size space while staying as low as possible on the distortion space, on the distortion axis, I'm sorry. And it does this by optimizing this cost function that we can see here. And the first thing in this equation accounts for the total size in bits that are needed to encode a coefficient. So we will start with the size right now. And we will explain this looking at an example. We'll look at an example of AC coefficient sequence, and these are quantized coefficients. So we have the 3, 0, 0, 8, 0, 4. Now, while encoding this, there's basically two things to keep in mind. First is that only the non-zero coefficients plus the number of preceding zeros are actually encoded. are encoded together. So we would encode the 3, we would encode the 8 together with 2 preceding zeros, and we would encode the 4 together with 1 preceding zero. Now, the second thing to keep in mind is that if we look at the bit stream, we can see that the non-zero coefficients itself are actually not Huffman encoded, but they are represented using variable length here in this bit stream. So the 3, the 8, and the 4 are represented using variable length. What we are left with in between now are the so-called control bytes. And the control bytes hold information about the number of preceding zeros and the bits that are needed to encode the variable length coefficient value. Now, these control bytes, we can produce them using this, let's see, using this table here on the right. So on the vertical axis, we have the number of zeros, and on the horizontal axis, we have the bits that are needed to store a coefficient value. So again, looking at our example, let's see. Looking at an example of this, we know, okay, we have 2 preceding zeros, so we would look at this line, and we need 4 bits to encode the number 8, so we look at this line. And that leaves us with 36. And 36 is the index in our Huffman table that is stored in the image that holds a symbol which we will use. So actually the variable length encoding coefficients are not Huffman encoded, but the control bytes are. And we end up with a bit stream of alternating control bytes and variable length encoding, variable length encoded coefficient values. Now, most JPEG tries, or Trellis tries to optimize that. And to optimize that, it uses this table. We will use this, we will call this table our size tree from now on. Because what it does is it contains coefficient values that are grouped in rows by the number of bits needed to represent them. So Trellis now tries, so for example, this is probably understandable. The size group number 4 holds all coefficient values that can be encoded at length 4. So all coefficients from 8 to 15. Sorry. Now, what Trellis tries to do it tries to reduce the total bits, the total number of bits that are needed to encode a bit stream or a sequence of AC coefficients. So what it does is it checks if it can change the non-zero coefficient values in a way to replace, it tries if it can replace the non-zero coefficient values with other coefficient values with the highest value of every lower size group. So that will be, for example, if we are looking at the 8 now, Trellis checks if it can encode it with 7, 3, and 1. It doesn't check if it can encode it with this, but it calculates the size that is needed if it would encode it with this candidate coefficients or alternative coefficient values. And now, as an example, we would encode it with, we would change the 8 to a 7, and we can see that we can save 2 bits. Now, Trellis also tries to increase the number of zeros. And in this example, we would replace the 3 with a 0, and that would save another 4 bits. Of course, we cannot do this arbitrarily. We also have to take into, but we can do this arbitrarily without destroying the image, of course. This is why we also look at the distortion. So the distortion is based on the square error between the unquantized coefficient value and the dequantized coefficient value. And it is multiplied with a lambda, with a subband specific lambda. And this lambda comes from the perceptual model that MOS-JPEG uses. The perceptual model is a variant of the PSNR HVS, and HVS in this case stands for the Human Visual System. The assumption is that the quantization table is a good approximation of this human visual system, and the advantage of the model is that it is additive in the DCT domain, so no transformation to the spatial domain is needed. The lambda is scaled, so that is scaled to the bits, so that it can be used in this cost function. And the third part of the equation here is the distortion of preceding zeros, zero lengths. Right, now let's look at an example of the whole trellis quantization. We have, again, an example sequence of AC coefficients, and we now want to optimize the coefficient at index 4. So we have an unquantized coefficient of 540, and we divide it by the quantization factor 72, and we round it to the nearest integer and end up with a coefficient value 8. Now, again, we use our size tree here on the right to look at alternative coefficient values of shorter encoding lengths. We do that and we calculate. So here we, again, as before, we would look at the 7, the 3, and the 1. For the sake of time, we will now only look at the 7 and space also. So what we do is we calculate the size. Like before, we can save 2 bits, one for the variable length and one in the control byte. Oopsie. Right, so next we look at the distortion. So we take our distortion equation and we evaluate it, and we can see that in this case, the distortion is exactly the same in both cases. And the reason is that the quantization error is exactly half of the quantization factor. So that means the cost, if we look here, so the cost in the end is actually lower for the candidate 7, for the coefficient value 7. I told you that Trellis also looks if it can increase the zero runs. So we try that out and we can see that the cost is higher in every case. So we will not do that. For completeness, we can also have a look at the remaining alternative coefficients 1 and 3. And we see that, yeah, so the cost for them, they do not only leave the size distortion space, but also our slides. So we will, of course, not use them. Now that we see how this works, let's look at the implications that these changes have for the field of steganography and steganalysis. So what we can see here is the frequency distribution of the first AC subband of 100 grayscale images that are compressed using baseline JPEG. And as we would expect it for natural images, it approximately follows a Laplace distribution. Now, if we use the exact same images and compress them using MOS-JPEG with its trellis quantization, we get this distribution. And what we can see is that trellis amplifies the zeros and the maximum values of shorter encodings. So remember that that 7, or well, actually 1, 3, and 7, and 15, and 31, they have just a higher frequency, or they occur more often. And while they occur more often, outer neighbors occur less often. Now, this has implications. So, for example, on the one hand, there's known steganographic embedding methods these trellis artifacts resemble the changes that are introduced by known steganographic methods, and a detector that is unaware of MOS-JPEG images might classify them as false positives. And on the other hand, a steganographer might mimic the MOS-JPEG artifacts in order to fool the detector that is aware of MOS-JPEG artifacts. So yeah, we have implications there. Now let's also turn to digital image forensics. I told you that MOS-JPEG also uses something that is called scan script optimization. And what it does there is it searches through roughly 1,000 scan script variants and decomposes the scan script, which produces the shortest output size for this specific image. So the scan scripts are actually content dependent. Now we wanted to know which scan scripts are actually there, which we can find in the wild. So what we did is we took the Folkheim dataset, which has approximately 23,000 images, which are captured from 27 different smartphone devices, of which 97% are in progressive mode. And the images, they were sent via Facebook, Telegram, Twitter, WhatsApp, and Instagram. We extracted the scan scripts, and what I didn't tell you is color images actually have 3 scan scripts. So one scan script for each channel. And to our surprise, in this Folkheim dataset, we only found 3 distinct scan scripts. And another surprise was we were able to link those scan scripts to the social media platform that the images were sent over. So while Facebook, Telegram, and Twitter, they all use the same default standard scan script, WhatsApp and Instagram use distinct scan scripts. So every image that was sent via WhatsApp used this exact scan script. This one. And all images that were sent via Instagram use this distinct scan script. So that means that we can potentially use the scan script as an indication for platform identification. Moreover, if we have an image and extract the scan script, and we know that the scan script is optimal for the image content, we can know that this image was potentially or probably compressed using MOS-JPEG. Yeah, so this already brings me to the end of my talk. So we identified the root causes for the artifacts that are introduced by MOS-JPEG. We discussed the implications for the fields of steganography and steganalysis and for digital image forensics. And I want to mention that MOS-JPEG calls into question the reliability of established methods in steganography, steganalysis, and image forensics. And I want to say that the community should incorporate this knowledge about MOS-JPEG into future research in order to improve the reliability of its methods. And yeah, so if you have any questions, I'm very happy to answer those. Also, I want to mention Uncover, which is the research project this research is funded by. And yeah, you can also, if you come up with questions later, yeah, send me an email. I'm happy to answer.